Inside this crystal lattice, electrons are stationary. The interior is a vacuum. Yet at the boundary, the surface sustains an unstoppable flow of electrons. For 80 years, we classified solids based on the energy gap. This gap represents the finite energy required to move an electron from a bound valence state to a mobile conduction state. In an insulator, this gap is large. The occupied and empty states are separated by a void, preventing the flow of electricity through the bulk of the material. We have discovered a phase of matter that complicates this definition. It possesses the bulk energy gap of a conventional insulator, yet its edges host gapless, conducting states that remain active regardless of the interior's resistance. These conducting states are a mathematical consequence of the bulk. The specific way the quantum wave functions are arranged in the crystal forces the surface to become a metal. This forces a shift in how we define phases. While Landau's traditional approach characterized matter by the symmetries it breaks, these materials are defined by their topological order, a property that remains locked as long as the system's internal energy gap stays open. A conventional insulator is topologically equivalent to the vacuum. You can imagine a process that smoothly changes the material's parameters until it disappears into empty space without ever closing the energy gap. In geometry, topological invariants describe properties that survive deformation. A sphere and a donut are distinct because you cannot turn one into the other without tearing the surface. This whole count is a quantized invariant. In a crystal, we calculate a similar invariant for the electronic bands. By integrating the Berry flux, a measure of the wave function's curvature, across the Brillouin zone, we derive a quantized number called the Chern invariant. The integer quantum Hall state is the first observed material where this invariant is not zero. It is an insulator that is mathematically distinct from the vacuum. Applying a strong magnetic field to a two-dimensional system forces electrons into cyclotron orbits. These orbits form quantized Landau levels, which function as a band structure with a non-zero Chern invariant. To move from a trivial insulator to this quantum Hall state, the material must undergo a transition where the energy gap closes and reopens, effectively tearing the quantum geometry. Consider an interface where a topological material with an invariant of 1 meets a trivial insulator with an invariant of 0. The bulk boundary correspondence dictates that if the topological invariant changes across an interface, the energy gap cannot remain intact at that boundary. To transition between these two distinct geometries, the conduction and valence bands must intersect. This intersection occurs exactly at the physical boundary. This intersection creates a bridge across the gap. Electrons can now move through these states, which are physically restricted to the edge of the material. In the quantum Hall effect, these edge states are chiral. Because of the magnetic field, they move in only one direction. This prevents them from bouncing backward, making them highly efficient conductors. However, these chiral states require massive external magnets. This makes them difficult to integrate into standard electronic devices that rely on intrinsic material properties. This leads to an essential question. Is it possible to create these protected conducting states using only the internal properties of a crystal without an external magnetic field? Elements with high atomic numbers provide the mechanism: spin-orbit coupling. This relativistic interaction creates an internal effective magnetic field that couples an electron's spin to its orbital motion.
In a system that preserves time reversal symmetry, we focus on special points in the momentum space, where the electron's momentum is its own negative. Kramer's theorem states that for spin 1/2 particles, time reversal symmetry forces a twofold degeneracy at these points. The bands are physically pinned together at these locations. If the bands connecting these points cross the Fermi energy an even number of times, they can be pushed out of the gap by small perturbations. This is a trivial insulator. If the bands cross an odd number of times, they become trapped. There is no way to remove the intersection without breaking the time reversal symmetry that pins the bands at the special points. This binary choice, even or odd, defines the Z2 invariant. A material is either a 0, meaning it is trivial, or a 1, meaning it is a topological insulator. The Z2 invariant proves topological protection can be generated intrinsically. The spin-orbit interaction creates the required tear in the band structure without external magnetic interference. This theory was tested using quantum wells of mercury telluride. In this system, the thickness of the material layer determines the alignment of the electronic orbitals. At a thickness of 6.3 nanometers, the S-type and P-type bands cross each other. This inversion flips the Z2 invariant, spontaneously transitioning the material into a topological state. These measurements from the Würzburg group show the resistance of different samples. For the thicker, inverted wells, the resistance hits a stable plateau as the gate voltage moves through the gap. This plateau corresponds to a quantized conductance of 2e²/h. This is the hallmark of the quantum spin Hall effect, occurring at zero magnetic field. The conductance is the result of helical edge states. Along the same edge, up-spin electrons move in one direction, while down-spin electrons move in the other. This helical flow is robust. To bounce off an impurity and reverse direction, an electron would have to flip its spin. Because the material preserves time reversal symmetry, this spin flip is forbidden, allowing the electrons to flow around obstacles without losing energy. This two-dimensional effect scales into 3 dimensions. A strong 3D topological insulator possesses an insulating interior but a conducting 2-dimensional surface. The surface states form a single Dirac cone. Its energy dispersion is linear, with bands meeting at a single point. This leads to spin-momentum locking. An electron's spin is always fixed perpendicular to its direction of travel. Knowing its path reveals its exact spin. While graphene has 4 such Dirac points, the surface of a topological insulator has only 1. This effectively creates half of a standard 2-dimensional metal, localized entirely on the surface. This framework has led to a systematic classification of matter. By analyzing systems based on their spatial dimension and internal symmetries, physicists have identified 10 distinct classes of topological insulators and superconductors. The most significant application arises at the interface of a topological insulator and a superconductor. The proximity effect induces a superconducting gap in the topological surface states. This interface supports Majorana fermions, quasiparticles that are their own antiparticles. They always appear in pairs, with information for a single quantum state shared between them. This shared, non-local storage is the key to stability. Because the quantum information is not held in a single location, local noise or heat cannot see the entire state. This protects the data from the decoherence that typically destroys quantum calculations, providing a physical foundation for a fault-tolerant quantum computer.